Hello. Alright, welcome back. Second video in 8.2. Mole to mass, or mole to Avogadro's number, or mass to Avogadro number calculations and conversions. Big thing here is to know your technique. So I just went and looked at YouTube, and only 35 out of 104 of you in the summer class have actually viewed how to do the conversions for metrics. Go back and watch that video, because if you can't do the conversion technique, you can't do this. If you do know how to do the conversion technique, then this is actually really easy. Alright, so why mole to mass relationships? Well, in the last video we said that we don't have a molometer in the lab. What we have is a balance, a scale. So we can weigh out materials. We can't count the particles. So really this relationship here is pretty intimate. For instance, if we have 1 mole of water, last video we calculated that would be 18.015 grams of water, and that a mole represents 6.022 times 10 to the 23rd molecules of water. So this video is about being able to interconvert between those three ideas. So this number is the Avogadro constant. You do not have to memorize that number. That'll be given to you on the formula sheet. And then anytime we want to convert to or from grams back to moles, we can find that information on the periodic table, because the periodic table, they've already multiplied by Avogadro's number, the real mass, and now we have a mass that we can use that's connected to the mole. So for instance, suppose in an experiment we needed 8.00 moles of water, and I want to know how many grams of water that would be. So how many grams of water? Don't know. Alright, so we're going to use our technique for conversions. We always start with what they give us. Now you can abbreviate the mole MOL, or you could put a lowercase m with a line over it. I kind of do it interchangeably because I'm limited to the space here on the tablet. But I did want you to see that. So we're going to multiply by a fraction, and we're going to put our units in, moles of water, to get them to cancel out. Now, is there a relationship between moles and grams that we could put in the numerator? And the answer is yeah, right up here in the introduction. The periodic table allows us to make that conversion. So I'm going to put grams of water in the numerator. Now I'm going to put in the numbers. For every 1 mole, I have 18.015 grams of water. And now I can just use the calculator to complete the problem, because moles of water cancels. We're left with grams. So 8 times 18.015 divided by 1, I get 144.12. How many sig figs? 3 sig figs. So this is going to be 144 grams of water. Easy, right? Don't overcomplicate it. This is easy. Alright, so what if we go in the other direction? Let's say we go and we measure out, I don't know, let's do 250 grams of table salt, sodium chloride. So I want to know how many moles of table salt did we measure out. Okay, again, our technique, start with what they give you. 250 grams NaCl. We're going to set up our fraction, get the unit to cancel out, grams NaCl. Now notice in my work, number, unit, chemical label. Number, unit, label. You have to have all three things in your FRQ. So how many grams would be 1 mole of NaCl? We calculated that in the last video, but you could calculate that again by looking it up on the periodic table. We look up sodium, which is 22.990. And we're going to add the chlorine, which is 35.453, and we get a mass of 58. I'll do this in green. 50. Stand. Anyway, 58.443 grams. So we do 250 divided by that, and we get 4.277672262, but I'm only going to use 4 sig figs. The 0 to the right of the decimal is significant. That makes the 0 in between significant, so all 4 of those digits are significant. So I'm going to round this up to 4.27 4.278 moles of sodium chloride. Make that a 7. Okay. So grams to moles, moles to grams, pretty easy because we can find the conversion factor on the periodic table. All right, what if, for some ungodly reason, and I don't think this is a very important calculation, but every chemistry course teaches it, college professors expect you to know it, etc. What if we had 1.67 moles of water? And for some reason, we're just wondering, hey, how many molecules of water do we have? All right, so when they talk about the number of atoms and the number of molecules and actually counting the number of formula units, which unfortunately is abbreviated FUs. So atom, molecules, FUs, that's when you're going to use Avogadro's number. So how many atoms is a mole? 6.022 times 10 to the 23rd. But they're not asking for a mole, they're asking for 1.67 moles. So we know we just have to take that number, Avogadro's number, and multiply it by 1.67. But here's how the technique looks. Again, start with what they give you. And we're going to multiply by a fraction. Let's get moles of water to cancel out. And let's convert that to the number. Oh, I didn't leave myself a lot of room, did I? Molecules. That's supposed to be molecules of water. Now I can put in the numbers. For every 1 mole of water, I have Avogadro's number of molecules. And then here's where knowing how to do scientific notation on your calculator helps. 1.67 times 6.022 exponential key. 23 for the exponent. And I get 1.005674 times 10 to the 24. I'm going to use 3 sig figs. Now, this comes out to be 1.005. Most of you take a 5 and round it up, but the rule actually is that you always round towards the even number. So we shouldn't do 1.01 times 10 to the 24. We really should do 1.00. But since that makes all of you uncomfortable, I am going to do 1.01 because that's the rule that you probably learned in middle school. I know, you didn't learn anything in middle school. Molecules of water. So anytime the question involves the number of atoms, the number of molecules, number of formula units, we're going to use Avogadro's number. Let's try one more. Let's go in the opposite direction. Suppose we have 3.4 times 10 to the 25th atoms of, let's use chromium. And I want to know, hey, how many moles is that? Moles of chromium. So again, our technique, start with what they give you. 3.4 times 10 to the 25th atoms, chromium, number, unit, label. We don't have to write in the preposition of. It's assumed. Atoms of chromium. And we're going to set up our fraction. Okay. Put atoms of chromium in the denominator. And we're going to convert that to moles of chromium. Alright, so now we can put in our numbers. For every 1 mole, we have Avogadro's number of atoms. And again, knowing how to use your calculator will help here. 3.4 exponential 25 divided by 6.022 exponential 23. And I get 56.45964796. And I need to do 2 sig figs. So this is going to be 56 moles of chromium. All right, last type of problem. Here we go. Easy. Don't overthink. Don't overcomplicate. Use your technique. If we have 500 grams of water, I want to know how many molecules. All right, so now we need to do a complex conversion here. We can't go directly from grams to the number of molecules because there's no relationship between grams and moles. Certainly a mole of trucks are going to weigh more than a mole of feathers. So what do? Well, you go back to the base unit. And the base unit in this chapter is the mole. So let's convert back to the mole. Start with what they give us. 500 grams of water. We're going to convert back to the mole. Grams of water versus moles of water. Right? 1 mole of water, we already calculated, was 18.015 grams. Again, you look up 2 hydrogens on the periodic table, you add it to an oxygen, that's how you get your 18.015 grams. Now, we're going to set up a second fraction. And we're going to say moles of water in the denominator to get that to cancel. And then we're going to go to molecules, and again, I didn't leave enough space there. Molecules of water. All right, so 1 mole gives us 6.022 times 10 to the 23rd molecules. All right, so let's calculate this then. 500 divided by 18.015 times 6.022 exponential 23, and that comes out to be 1.671384957 times 10 to the 25th. How many sig figs? This is 5, this is 4, and this is 4, so we're going to use 4 sig figs. 1.671 times 10 to the 25th molecules of water. And why anyone would ever want to know the actual number of molecules. Now, moles are important, but the actual number of molecules, that kind of seems silly to me. Now, we could go from atoms or molecules or formula units back to grams, so I'm going to let you try that, and that's going to be my last problem for this video. What if we had 8.6 times 10 to the 24th formula units of sodium chloride? I want to know how many grams of sodium chloride should we weigh out. Alright, so go ahead and pause the video and work it out, and then come back and check your answer. I'll wait. Hey, I'm back. Alright, so let's use our technique. Alright, did you try to cancel out the unit? Did you convert back to the base unit, the mole? And from there, did you cancel out the moles and convert them to grams? Notice, I could do this to set up the fractions and just put in my numbers later. 1 mole is Avogadro's number of formula units. 1 mole is, I'm going to add sodium, 22.990, to chlorine. You think I would remember since I've done this so often. To chlorine, which is 35.453, and I get 58.443. I knew it was 58 point something. Okay, so now we get out our handy dandy calculator and we just do the math. 8.6 exponential 24 divided by 6.022 exponential 23 times 58.443, and I get 834.6227167. So how many sig figs? Only 2. So this is going to round down to 830 grams of sodium chloride. Number with correct sig figs, unit, and label. And that's all there is to it. Please do not overcomplicate it. The key to this is understanding your technique. So again, go back and look at that video from chapter 2.81 on conversions.